For our simple rational functions part 2 lesson, we've looked at horizontal and vertical asymptotes, but now we're going to be looking at open holes like we looked at in previous chapters. Many rational functions have removable discontinuity, which is an open hole. So with removable discontinuity, it will appear as an open hole on the graph. It occurs at an x value that makes the denominator and the numerator equal to 0. So just to write this out, well, it shows like here, I have 0 divided by 0. So if I have a limit and x is approaching, again, a certain value, so x is approaching a of my function, I'm going to end up with an answer of 0 divided by 0, right? Same as there. And that's an indication that you have an open hole. So whenever I get 0 divided by 0, it means the rational function is indeterminate for this, at this x value, right? For a specified x value, and then I have an open hole. So to sketch a graph that might look like this, I have to state any restrictions on the variables. Vertical asymptotes, now we have removable discontinuity and any restrictions on the y value. So we've done this before, just not the removable discontinuity in the last lesson. State the behaviors that are happening around the asymptotes and around the open hole we'll be looking at. And everything else is the same as well as the last lesson. Figuring out our x and y intercepts, our critical numbers, the intervals of increase or decrease with the first derivative chart and classifying them. And the intervals of concavity and points of inflection with our second derivative chart, and then sketch and state the domain and range. So let's just jump right into, again, this is a long example. Probably the number of sheets here is, again, I would write a little bit on the smaller side. So analyze the following. I'll see how far I can get here without having to erase anything. So I have my function, which is a rational expression, 2x minus 4 on top and x squared plus 3x minus 10 as the denominator. So as always, we want to find step 1 is our restrictions on x. And it's good if you write this out for me too, right? Instead of just going right into the work, right into the math, explain to me what you're doing so I can follow the steps on a test or assignment. So what are my restrictions on x? So it's always that the denominator cannot equal 0, right? So my denominator here is x squared plus 3x minus 10 cannot equal 0. So is that factorable, right? Can I find two numbers that multiply to negative 10 and will add to 3? 1 times 10, 2 times 5 is a difference of 3. If I want to add to a positive 3, if it was positive 5 and negative 2, that would work, right? So I've got x minus 2 and x plus 5 cannot equal 0. So then separating them, if x minus 2 cannot equal 0, then I bring that negative 2 over, then x therefore cannot equal 2, right? 0 plus 2. If x plus 5 cannot equal 0, then x cannot equal negative 5, 0 minus 5. So these are my restrictions. X cannot equal 2 and x cannot equal negative 5. We don't know what's happening at those restrictions. We just know that they are restrictions. So what we want to do now is plug these into our limit expression to see what's happening around them, right? To determine what's happening. Plug these, sorry, that's an S, into our limit expression. So what is our limit then? As x is, we've done everything in like numerical order. So let's say like negative 5 and then 2. So let's just, it doesn't really matter here, but let's just start with a negative 5. So our limit as x is approaching negative 5, we write out our original expression, x squared plus 3x minus 10, and we plug in negative 5 when we see x. So 2 times negative 5 minus 4 all over negative 5 squared, 25, plus 3 times negative 5, negative 15 minus 10. And I have here negative 14 over 0. So here is our number over 0, like in the last lesson as well. A number over 0, anything divided by 0, right? Try it on your calculator, you get an error. This does not exist. This is not what we're talking about up above. We didn't get 0 divided by 0. We got a number divided by 0, right? So that means I have a vertical asymptote at a value of x equals negative 5. Make sure you don't forget the negatives. So let's check out the other limit. What's happening around my value of 2? The limit is x is approaching 2. Again, write out your expression. X squared minus 4, x squared plus 3x minus 10. Plug in 2 for x. So that'd be 4 minus 4. That's a 0 on top, right? 2 squared is 4. Plus 3 times 2 is 6. So that's 10 minus 10. And you can hopefully see here I do have a 0 divided by 0. So that would be today's lesson, which indicates that it's an indeterminate, which means that I have an open hole. Okay, so two different things. I have a vertical asymptote happening at x equals negative 5, and I have an open hole happening at x equals 2, which I can then, you'll see that when I graph all the way at the end of the question here, right? So just to point out, make sure you're paying attention to this statement. When you have an open hole, so right here I have an open hole, this expression has an open hole associated with it, with removable discontinuity, then that means that my original function can be simplified further. And I can use that simplified expression for the rest of my question. So for example, I want to get the coordinate point of this open hole, right? I know that at the x value it's 2, but what's my y value? So I know where to put that open hole. If I can simplify this first and just make it easier on me, then I can use that to get the coordinate point of the open hole. So that happens all the time. When I have an open hole with removable discontinuity, it means that my original function can be simplified further. So why don't we go ahead and simplify that function further so we have it a little bit easier to work with from now on. So if I look at the top, the numerator, I can factor out a 2, and I would get x minus 2 in the brackets there. And I already factored the bottom, right, into x minus 2 and x plus 5. Then I can see, because they're all multiplied, I can cross out the x minus 2's, and then I'm left with just a 2 on top and just an x plus 5. Well, that seems easier to work with than my original function, right? But keep in mind that you're going to have the same restrictions. My restrictions are still on the original denominator, right? Or else I would get rid of all this work I just did, right? So I have a restriction at x equals 2. I have an open hole, and I have a restriction at x equals negative 5. I have a vertical asymptote, right? So let's figure out the coordinates just to squeak in here of the open hole. Because we know the x value, we don't know the y value, but now we have an easier function to work with. Coordinates of the open hole. So here's my function, f of x equals 2 over x plus 5. I know x equals 2, so just plug in 2 into my function, in for x, into this new, this is my new expression that I can use, right, throughout. So 2 over x plus 5, 2 plus 5 is equal to 2 over 7. So therefore, the x value of 2 and a y value of 2/7 is the location of the open hole, right? Is my coordinate point. Location of the open hole. Okay, let me see if I can continue on down there a little bit. Slightly, I probably can fit the behavior around the vertical asymptote in here, and then I'll have to clear and move up, okay? So let's look at our behavior. And again, I'd like you to write this out for me too, so I can figure out what you're doing, right? So the behavior around, you can just say this, vertical asymptote. So my vertical asymptote is again at x equals -5. So behavior, we're looking at what's happening if I'm approaching from the left-hand side and what's happening as I'm approaching from the right-hand side for those limits. So the limit has x as approaching -5, but from the left, again, my original, like simplified function, by original, I mean the one that I can use now, is 2 over x plus 5. Now, if I'm approaching from the left, just to the left of -5, we can use like -5.001, let's say. So 2 over -5.001 plus 5. And again, this is where I don't actually need when I'm figuring out around my vertical asymptote, I don't need definite values. You don't exactly have to plug that into the calculator, but when I'm looking at figuring out my horizontal asymptote, I do. So I do end up with an answer of -2000, but really all we care about is that we have a positive on top, right? And then we have the negative is slightly bigger than the positive, so it'd be negative, and we would end up with a negative number. So what that means is that we would be approaching negative infinity. So just to write that out here, as x is approaching -5 from the left, as x is approaching -5 from the left, my y value is approaching negative infinity. So that will help us when we graph, right? And let's do the approaching from the right, and that's about all the room I have here. The limit as x is approaching -5, again, from the right-hand side. So just to the right of -5, we could use -4.99, -4.999, and we have to write out what our expression is here, is equal to 2 over, again, -4.9. I have 3 nines on my page, plus 5. But again, all we really care about is that there's a positive on the top. The 5 is larger, so we're going to end up with a positive on the bottom. So now we're approaching positive infinity, right? I have an infinite result. So that conclusion would be, as x is approaching -5 from the right, y is approaching positive infinity for when we graph. So again, just get that down or screenshot that quickly so that we can start talking about, we've done our vertical asymptote, we figured out what's happening around the vertical asymptote. Now let's move into figuring out if we have a horizontal asymptote, and we're going to look at end behaviors to get those y restrictions. I'll move this up just to here. All right, so end behaviors for the y restrictions. So again, explain to me what you're doing. Right now I'm looking at the end behaviors for my y restrictions. So we're looking at the limit now as we're approaching infinity. So as x approaches negative infinity of my simplified expression, x over 2 plus 5. And so again, I'm just picking a large negative number, if you remember. So we've been using 1,000, -1,000 up to this point. So why change that, right? So -1,000 plus 5. And that's, now this is where we do remember for our horizontal asymptote, we do want to get an exact number. So I end up with a number of -0.00201, which is obviously just below 0. So I'm approaching 0, but all I need to say is that I'm approaching 0 from below because I need to draw that in on my graph, right? So our conclusion then is, as x approaches negative infinity, as we're approaching infinity on the left-hand side, on the x-axis, we're going to be approaching y. Y is going to be approaching 0, but from the bottom, from below. This doesn't indicate left, it indicates from below, right? And now let's look at the limit as x approaches positive infinity on the right-hand side of my simplified expression. So this time we'll just use a positive 1,000. And so that answer is, again, if you're not writing out all the decimals, just put a dot on top of the equal sign. I have 0 decimal, 2 zeros after that, 00199, which means that that's very close to 0, but it's just above, right? We're just above 0. So just, above 0. So then our conclusion here would be, as x approaches positive infinity, y is approaching 0 as well, but from above. So again, that plus means from above. So if I'm hovering around 0 from the left side of the x-axis, if I'm hovering around 0 from the right side of the x-axis, then therefore I do have a horizontal asymptote at y equals 0. Because nothing's ever touching 0, right? I'm approaching from the bottom and top, but never actually getting to it. Okay, so that takes care of my vertical and horizontal asymptotes and what's happening around those values. Let's go to x and y intercepts now. Let's go to grade 9, right? Here's my original function, f of x, but if I'm talking about x and y, I'm just making f of x equal to y equals 2 over x plus 5. And isn't that nice that we have this simplified expression instead of the original? And so we'll just let y equal 0. And again, like we've said many times here, just to show, right, if I'm cross multiplying, I'm going to have 0 times x plus 5, which is just 0, and then 2 times 1. So I get, wait a second here, I get 0 equaling 2. So what does that mean? Well, what was I trying to get? I was trying to get the x-intercept. So I was letting y equal 0. So if this statement doesn't make any sense, it means that it does not exist. I'm undefined. Which means therefore, no x-intercept is all we mean. We don't have an x-intercept. Okay, so that doesn't mean that we don't have a y-intercept. We have to try it out. Y-intercept, let x equal 0, write out my original simplified expression. And when I see x, I put 0. So this is just simply y is equal to 2 over 5. So I do have one existing here. So therefore the point, again, when x is 0 first, y is 2 over 5. That's my y-intercept. 0 and 2 over 5. Okay, I'm just debating if I should fit in the critical numbers. I can start, I guess, right? To start working on my critical numbers. And again, write that out for me. That we're going to figure out our critical numbers now. So in order to do that, I need to get the first derivative, right? So if I write out my simplified expression, 2 over x plus 5, and let's get the derivative of that. So this is what? This is a rational expression. We've got a numerator, denominator. We're going to be using quotient rule on this, right? So the derivative of the top, again, the derivative of a constant is just 0. Make sure you write that in though. 0 times the bottom exactly the way it is, right? Minus quotient rule. Derivative of the bottom, which is just 1, times the top exactly the way it is, all over the bottom squared. So again, 0 times anything just gets rid of it. That's 0. So I'm left with a negative 2 on top, right? Negative 2 over x plus 5 squared. And then if you remember, I set my derivative equal to 0. So same thing as on this side. I don't know if I'm going to write it out every single time, right? But I would have 0 times the denominator, which I would just get 0 equaling what now? Negative 2. Same thing as over here. 0 doesn't equal negative 2. So what does that mean? I was trying to figure out what? I was trying to figure out what my critical numbers are. The statement doesn't make sense, so therefore I have no critical numbers. Okay, so therefore I have no critical numbers. Now I'm just going to say this before I clear the screen here and move on, because I'm guessing that what you would be thinking is, okay, if I have no critical numbers, then I don't need to do a first derivative test. I don't need to do a chart, right? So I just want you to think about this. Do we still have a function? Do we still have something to graph? That function exists, right? So I still have a function. So I still have to do an interval chart because I have a function. So that function, something is going to be drawn there, right? So that function, it just means that function might be always increasing, or it might be always decreasing. So if I don't have critical numbers, what would I use in my first derivative test? I'm going to be using the restrictions that I have. I know that I have some, I don't want to call it critical numbers, right? But important. I know I have something happening around x equals 2, right? And I know I have something happening around x equals -5. So that's what we'll use. And let's figure out what's happening around those restrictions. So that's still going to be helping us to graph. Do I have the function increasing or decreasing? And is there a change? But is it going from increasing to decreasing? What is happening there? I believe we just have that next page with the graph. So I'm going to stay on this second page to fit everything in. So like I said, we will always still create a first derivative chart. So let's do our number line so we can kind of mentally see what we're doing here. So from -infinity to +infinity, and again, this is our x-axis. So what did we say? We said we figured out that something was happening at -5 on x, right? We're talking about our x values, and something's happening at, +2. So at +2, if we go up to the top, what was happening at x equals 2, that was our open hole. So we will just call this OH. And at -5 was our vertical asymptote, right? And I don't have any other critical numbers to add to here, but I need to see what's happening around those values. So I have 3 intervals. So my chart's going to have 4 columns. So the first part of the chart is going to be factors of the derivative, the factors that we received. My first interval is from -infinity to -5. My interval in the middle is from -5 to 2. And then from 2 all the way to +infinity. And again, you can use straight lines here if you want. I just find me to go and hit that button to hit the straight line every time, it's honestly going to make the video even that much longer. So if I go look at my factors right before, I'm just going to write off, right before I set it equal to 0, I had -2 over x plus 5 squared. So then my factors are, again, you separate the numerator as a factor and then the denominator x plus 5 squared. And then I have my overall sign for the first derivative. And does that mean that I'm increasing for short here or just decreasing along the original function? And again, I'm just going to make these as straight as I can. I mean, if yours look like this on a test, again, if it looks horrible, you know you're writing. If I can't read it, that's not too bad, right? There's nothing there that's illegible, I think. I'm thinking that. From -infinity to -5, so I need a value that's smaller than -5. So let's say I choose -6. Well, -2 here, if I plug -6, you can't into -2. That -2 is just going to be negative all the way along, and it's just a constant, right? So that makes it easy. If I plug -6 into the bracket and add 5, -1 squared actually brings me to a positive. A negative, again, this is a quotient, a negative divided by a positive, right? Negative divided by a positive gives me a negative, which means I'm decreasing along this part of my function. Now, a value between -5 and 2, 0 is in between there. It's always an easy one to choose. 0 plus 5, and then squared would be positive. Negative divided by a positive is negative, and I'm decreasing along that interval of my function. And between 2 and infinity, I could have picked anything. 5, I'll just pick one larger. 3, the next whole number. 3 plus 5, 8 squared is positive. A negative divided by a positive is, do you see what's happening here? Negative. So like we said before, so I'm decreasing all the way along this function. So I don't have, well, I'll wait till we get to the second interval chart. But I need to state what's happening around this value of -5. So I have here my vertical asymptote at x equal to -5. And then here at 2, I have my open hole, right? Open hole at, and I could put the coordinate point since I know it's 2 2/7. Okay. So now let's look at our possible points of inflation. Inflection. I don't know why I'm saying those. Sometimes I say point of intersection just because I write it as POI. I'm just trying to get these videos. If I talk even slower, it'll take up even more time, right? So sometimes I'm talking faster than I'm thinking. Possible points of inflection. So that's why, at least if I say it wrong, I'll write it out properly there for you. So we know that's the second derivative. So the first derivative, copy it from the right above you on the page or a previous page that you had it written down, was -2 x plus 5 squared. So again, we're going to use the quotient rule here. Just seeing how much room. I'll go over here, see what happens. Second derivative, derivative of the top, 0 times whatever the bottom is, minus, for quotient rule, derivative of the bottom. So you bring that 2 out in front, 2x plus 5, again to the power of 1, but you don't need to write that down. Multiplied by the derivative of the inside is just a 1, but if you still put that down, I know that's what you're doing, so I'd like you to. Multiplied by the top, all over the bottom, squared. So x plus 5 is already squared. Don't get confused about that. Then put square brackets and square it again. And then it's just a matter of cleaning things up the best I can, right? So 0 times this is just 0. And then I have here what's going on. I have -2 times 1 is a -2 times another -2 is a +4. So I have the +4 still with the bracket, x plus 5 multiplied by x plus 5 all over x plus 5, again, 2 times 2 to the exponent of 4. And then here I can see if I have a similar, right, x plus 5 and x plus 5, I can get rid of 1 on the top and 1 on the bottom. That would turn that into a cubed. So just to rewrite it again, I would have here 4 over x plus 5 cubed. So not too bad. That simplified nicely. So that's our simplified form of the second derivative. Then we set it equal to 0, right? 0, 4 over x plus 5 cubed. So again, 0 is really just going to be equal to the numerator because 0 there, right? Which, what's happening here again? Does 0 equal 4? This does not exist. So just changing my color here. So that means that I have, therefore, no points of inflection. I have no inflection points. So I have nothing, no twists, right? Nothing where it's going from concave down and then along the same curve, kind of twisting and shifting to concave up and then shifting to concave down. I don't have any of those inflection points. But I want you to think, I still have a function, right? So there still is concavity happening. We saw in the first chart that I'm decreasing. So am I possibly concave up the whole time, concave down the whole time? I still have concavity. So again, I still do need to complete the second derivative chart. So that's what I'm doing here. So if I again have my x-axis where I have positive infinity and negative infinity. And again, the only values I have to mark down here are those -5 and 2, which is my open hole, and my vertical asymptote. I'm looking at it in terms of the second derivative now along those intervals. So again, I'm going to have a 4-column chart. So I need my factors of the second derivative. I put G, I think it's F. Factors of F double prime of X. And then I'm going from the interval of, same as before, negative infinity to -5, -5 to 2, and 2 to positive infinity. And we're almost there. Basically, after this, we just write our conclusion of what, like, you can see we have limited information here for graphing, but we will have enough. So my factors, again, before I set it equal to 0, my numerator was 4 and my denominator is x plus 5 cubed. And then I have my overall sign of the second derivative. And here it's, does that mean I'm going concave up or down along my original f of x function? Oh, I should put my rows in here or else it's going to get pretty messy. All right. So values, I can pick the same ones I did before, right? -6. Again, if this is a +4 constant, it's going to be positive all the way along. -6 plus 5 is a -1. -1 cubed is negative. A positive divided by, right? I'm dividing. Divided by a negative is a negative, which means I'm concave down. Let's pick 0. I believe that's what we had last time, right? So 0 plus 5, 5 cubed is going to be positive. That's going to be positive. Oh, look what's happening here. I am switching to concave up. So you might be thinking, well, how do I switch from concave down to concave up without any points of inflection? And we'll get there. And then a number larger than 2. If I pick 3, 3 plus 5, 8 cubed is going to be positive. Positive divided by a positive. I'm staying concave up right there. So I go concave down to concave up to concave up. And what is happening here? Again, at this value where I'm switching from concave down, right, to concave up, it's actually a vertical asymptote. Because it's not a point of inflection is also a hint that I don't have that happening, right? So it's a vertical asymptote happening at x equals -5. And again, here I have an open hole. So I'm going concave up, smiling, right, this way, but somewhere along that concave up, I have an open hole at 2 2/7. So this is where let's list what we know. Now I'm going to switch to the graphing page. Let's list everything we know I find helpful. Besides, I wanted to just go up and look at step by step what you have. I just find, again, what if you missed looking in all the busyness of everything you wrote on all the pages? I like to have all the information right there beside the graph. So if I move this up, again, let's just go kind of starting at the beginning and list all the information that we would be putting on the graph. So list what we know. We did all that work. What did we find out? We found out we have a vertical asymptote at x equals -5. So I have to draw that in. We know we have a horizontal asymptote at y equals 0. So I have to draw that in. That's a 5. Just make it worse. X equals -5, y equals 0. I know I don't have an x-intercept, right? That one did not exist, but I did have a y-intercept at 0 2/5, which again, I could figure out where, 2/5 is 0.4, because again, that just helps when I'm graphing. And what else? The open hole is at 2 2/7, and that y value of 2/7 is basically 0.3, 0.29, but when we're graphing, we're not going to be that close anyway, so I can make it 0.3. I had no, I'm going to write up here, I have room. I have no local extrema. There was no max or min. But I still did the chart and I found out that I was always decreasing. That's important to know. You want to make sure your graph shows that. And I have no points of inflection. But I know from the second derivative chart that I am concave down like I'm saying, reading it from left to right, right? So I'm concave down until I get to x equals -5. Then concave up, and it stayed that way, right? Then the third column was concave up as well. So I just need to make sure when I'm drawing it that I'm concave down. So a frown, I'm frowning until x equals -5, and then I'm concave up, and then I'm smiling, okay? So I'm gonna see if I can zoom in a little bit on this graph because it looks a little bit small to me to graph it. So yeah, that's all we have. So let's try to graph it, and then we get our domain range. It always looks so nice after it's graphed, right? Zooming, let's see here. Maybe even a little bit more. Okay, that's probably, hopefully good enough. Let's do in order here. Let's do our vertical asymptote. Well, we have to figure out how I'm going to do my X and Y axis first, and a color for that. So again, you look at your X and Y values. So I have a vertical asymptote at X equals -5. So I obviously have to get over to the left to -5. My other X values are 0 and 2, and that's it. So, but I also have, yeah, I have a little bit of positive up to 2. So I basically want to put my Y axis in the middle, and I just want to have some negative and some positive values. So let's just say it's right here. Oh, I should have made that thicker. A thicker line, 1 second. Right here, let's go thick. Let's try that again. There you go. Hopefully you can't miss that. That's our y-axis. And then if I look at my, I've got a horizontal asymptote at y equals 0. I have y values very close to 0, 0.4, 0.3, and that's about it, right? So they're all positive. So I could even, yeah, I could even bring the x-axis down just a little bit. Not that it really matters because the numbers are so small. Okay, so let's go back here. Let's label our axis now, right? Make sure you're doing all that all the way from grade 9. You label your X and Y axis and also put your scale in. So I said we can go by ones on the X axis. So 1, 2, 3, 4, 5, 6. -1, -2, that would be -4, and that would be -6, right? I'm doing every one is 1. I'm just writing out every other number because again, if I wrote the numbers in between, it would just look a little too squished, right? And again, for my scale, if I have decimals, 0.4, 0.3, and then just 0, I might as well have my scale on my y-axis to be less than 1. So if I did it by 0.1, I could fit everything. All these are positive y values. So 0.1, 0.2, 0.3, 0.4, that line, 0.5, 0.6. I don't even think I need any higher than that. And then -0.1, -0.2, and -0.4. And again, I don't even think I'm going to be down there. Okay, so let's draw in our vertical asymptote. So let's do that in purple. I'll do that just, yeah, that thickness is good. I want it dotted, so I can't pick the solid line. I'm gonna have to do it freehand, so it's not gonna look quite as nice, but I'll try, right? So at x equals -5 right here, I'm doing a vertical asymptote. So you can just use a ruler and go, but make it a dotted line. And so here is my vertical asymptote at x equals -5. I should just write that underneath, right? Because I'm running out of room there. And then, so you could always check off, right? That part's been done. And then my horizontal asymptote is at y equals 0. So here's y equaling 0 is the x-axis. So I just have to draw on top of it. Again, this is why different colors help. So I can see that there's different colors. And so I have my horizontal asymptote at y equals 0, and that's done. Let's go here to our limits maybe and draw those in. So let's go back here. So as x negative 1, am I on the right page here? 3.4 Oh, sorry, I'm looking at the next video I'm going to be doing. Like, I don't have anything with negative 1. All right, so at x equals negative 5, yes, as x approaches negative 5 from the left, y is approaching negative infinity. So I need to put an arrow right here in this direction. And then as x is approaching negative 5, the vertical asymptote from the right, we're approaching positive infinity. So infinity, and then from positive, right here like that, from the top, from above the x-axis. And I also have here for my end behaviors for the horizontal asymptote that I figured out, as x is approaching negative infinity, as we go farther to the left on the x-axis, the y is going to be approaching 0, but from the bottom. And as x is approaching positive infinity, y is going to be approaching 0 from the top. So we have that, but we don't have the negative infinity will be here, and positive infinity will be on this positive side here. Because that kind of helps us with how I'm going to be graphing it, right? Oh, I just don't have, sorry. This one here, I'm not including my asymptote there to block me. So this one here, I missed that. To go back here for my horizontal asymptote. Where am I? So as we're approaching the vertical asymptote of negative 5 from the left, the y value is going to be going to negative infinity. So down here, as I'm approaching x equals negative 5, sorry, from the left, y-axis is going to be going down to negative infinity. And then as I'm approaching the vertical asymptote of negative 5, sorry, from the right-hand side, my y-axis is going to be going to positive infinity. So that would be right beside the vertical asymptote there. I just was using the orange line for some reason and not the vertical asymptote, but we got it fixed. All right, so what else do I have? I don't have any points on there yet. So I have no local extrema, so now I can put in my 2 points that I have, right? So let's do those in any color. So my y-intercept is at 0 and 0.4. So there's 0 and 0.4 right there, crossing the y-axis. And my open hole is at positive 2 for x and up to 0.3. So be careful because it's an open hole, right? Don't color it in. There we go. So now using the information also I have about increasing and decreasing and concavity, I can figure out how to graph the rest of this. But you can see how these purple arrows from my limits are really helping me, because if I'm starting here and I have to go through here and I'm ending there, but what happens here? So if I look at my first derivative chart, was every single column was decreasing. I'm always decreasing. So I'm going down, right? So here I'm going down and I'm decreasing and lining up with this other arrow. And for this one here, I'm going down and I'm decreasing. Again, I'm going through and the best I can here, and I'm going through there. That's not the best. That could have been, it's not gonna help. Trying to do that a little bit better. Again, if you use pencil, you can kind of adjust. Okay. And in terms of concavity, I'm concave down, so I should be looking like I'm frowning before x equals -5, before the vertical asymptote. So look, I am concave down. That is the, let's say, the right side of someone's frown, right? And then I'm concave up for all the rest of the time. I should be looking like I'm smiling after that. Here it's concave up. It's like the left side of somebody's smile, right? Looking at a picture of somebody. So that is a smile. So there you have, again, I would clean this up and I would erase, but if I erase, you can see it's going to be probably erasing like more lines, yeah, than I want to. So just with your pencil, go and just clean that up and pick the best line that you had. Here's my open hole to make it look continuous. And domain and range. My graph is done, now my domain and range. So my domain, it is a solid continuous line. We'll deal with the open hole, but x belongs to the set of real numbers. I know I have a restriction, so I can say such that. Now x would be continuing on forever on the left-hand side and on the right-hand side. So the only really restriction that I have is I don't have x happening anywhere along this vertical asymptote. So x cannot equal -5, and also x is not a solid solid dot at x equals 2. It's an open hole, so it's also not equaling 2. And for my range, we're looking at y belonging to the set of real numbers. Is there any restrictions here? Now, if I look at my horizontal asymptote here, this part of the function is approaching, but not touching. This part of the function is approaching and approaching, but not touching the horizontal asymptote. So this function actually is never going to hit y equals 0, right? So it won't hit y equals 0. The function will never cross it. And where else? Well, if I have an open hole here at an x value of 2, I also have a y value, right? That y value is never going to actually be going through 0.3. Or you could say, 2/7 to be more exact.